This is Chapter 3, Plate Tectonics, Lecture 2. And we will pick up with continental rifting. So we're going to observe what happens when continents rift apart or move apart. What we have here is an initial uplift from the rising mantle. We get stretching and faulting in that area that forms the rift. For example, the East African rift is like this. We have melting underneath. That forms magma. I'm going to tell you about the mechanism for that in the future. That can lead to seafloor spreading and the development of a new ocean basin like the Red Sea. The ocean widens further with spreading. If it keeps doing that for a very long time, you get the modern Atlantic Ocean. All right, so let's talk about convergence now. This is an ocean-ocean convergent boundary. That means one oceanic plate is converging with another oceanic plate. So, two oceanic plates move toward one another. We have what's called subduction. That's when one plate moves underneath another. That is associated with an oceanic trench right here. That's a low point. An accretionary prism here, and an island arc in the back. We'll talk about why that is. Okay. So first off, the trench forms where the downgoing plate flexes downward. Some of that material is scraped off. It forms an accretionary prism. There are, simply put, chemical reactions that occur when this slab moves down and subducts. It releases water from the oceanic crust. Water actually lowers the melting point of this material, and it causes melting of the overlying mantle. Not the slab, but the overlying mantle. And then some of that will rise up and erupt as island arcs. So there you have that. If you want, you can sketch this. Okay. When an oceanic plate converges with a continental plate, here's a model of how that works. We have a trench as well, just like with ocean convergence. Here, the oceanic plate is pulled down and subducted beneath the continent, forming that trench. Once again, the overlying mantle is partially melted. That results in volcanoes, oftentimes, and squeezing of the continent to form a mountain belt. So you have volcanoes, solidified magma present in the crust, and deformation, which gives you a nice mountain belt. If you like, you can sketch this as well. This is the Pacific Ring of Fire, it's called. You may have heard of that. We say that because there's volcanoes all the way around here. Very dangerous. What do you think could explain the overall pattern and distribution of volcanoes here? Well, there's different things happening on either side of this, although there are volcanoes on either side. So, what we have in the center, we've got oceanic plates in the Pacific subducted beneath plates to the west and to the east. The oceanic plates on the west side here are subducted mostly beneath other oceanic plates. That results in island arcs. Remember the idealized model that we had earlier with this chapter with oceanic convergence. That's Japan and the Philippines. In the eastern part, Subduction occurs with an oceanic plate beneath a continental plate. And so you get mountain belts with volcanoes. So there's volcanoes resulting from both tectonic activities, but it's different on the west side because this is ocean-ocean convergence and this is ocean continental plate convergence. That's why they're different. And you want to be able to explain that. It does come up in the quiz at least once. Okay. Continent-continent convergence. That's when a continental plate converges or hits another one. Okay. Before that might happen, let's say we've got an oceanic part of a plate. This is oceanic crust. That's going to subduct beneath the continent first. On this side, we call this the passive margin. It's not the edge of the plate yet. But over time, as this plate moves towards the continent, subduction brings the continents closer. An accretionary prism forms. There's a trench as well. Suddenly, the continents collide. So there's no more oceanic crust. It's been subducted. And we have two continents hitting each other. Those are going to form a large mountain belt, not unlike the Himalayas. Okay. Continental collisions have a wide zone of deformation. Parts of both of those plates are sliced off within the zone, but continental plates are buoyant, so subduction stops. There's not a lot of melting in the mantle. There could be some in the crust, so maybe you'll get some recrystallized magma, but volcanoes would be kind of rare in that situation. As these converge, the crust thickens a whole lot. And that will form a large mountain belt or high plateau like the Tibetan Plateau. Okay. That's where your pieces are sliced off in your elevated region. If you want, you can sketch this. To better understand transform boundaries and how they're related to divergence, we can look at a pizza that is cut in this manner, tavern style or whoever you like to call it. Okay, so this is one plate, one tectonic plate, and this is another one, and they are diverging. We don't, well, we kind of have arrows for that, but not really. Let's see. As they move apart, one in this direction, one in that direction, they're also moving horizontally past one another, and that creates transform boundaries. So to the right and to the left. And that's kind of the relationship between a divergent boundary and the accompanying transform boundaries. Transform boundaries link other types of plate boundaries. See that in a block diagram. You have a divergent boundary here, accompanied by the transform linking segment. And the Mid-Atlantic Ridge is obviously a good example for that. You have overall divergence, but with that, in these fracture zones, you see the transform boundaries, kind of zigzags connecting the spreading centers. The transforms link the spreading segments. All right, you can sketch that one as well if you like. It gets real complicated in Western North America. So we have a divergent boundary here, divergent, divergent, linked by these transform boundaries. And then a convergent boundary in the Cascadian subduction zone. If you go further south, the San Andreas Fault Zone is a transform boundary. All that being said, what moves tectonic plates? I mean, they're moving, but why? All right. So in this case, we have subduction. A subducting plate pulls the plate downward. We call that slab pull. It's the strongest force driving plates. The plate slides away from the high ridge. That's called a ridge push. And it's affected by other forces, such as convection, currents within the mantle, centers of upwelling mantle material, and by the tendency of the slab to sag backwards. So you can't just do one thing. There's a lot of things going on keeping this planet moving and its tectonic plates moving. A lot of energy transfer and movement at any given time. And I'll bring up this relative plate movement map. Plates can move in terms of centimeters per year, but some move faster than others. This diagram is supposed to represent, I guess, plates that either have less than 3 centimeters per year of motion, 3 to 9 centimeters per year, and then more than 9 centimeters per year. So the arrows get bigger. Got a lot going on between the Pacific and the Nazca plate. Same here with the Pacific plate. Same here. Quite a bit of movement. Let's see. Lesser movements along the mid-ocean ridge. Something in the middle would be like the Antarctic plate and the Australian Indian plate. We can also show direct measurements of plate motions. These arrows show the direction of motion with higher rates shown by longer arrows. It's measured by Global Positioning Systems, GPS. Some of the arrows are curved because some plates are rotating and because, of course, plate motion is occurring on a sphere, a spheroid shape that is our planet. So in what areas are the main plates moving and how are adjacent plates moving relative to each other? We got movement over here. At the same time, this one's moving away from it. At the same time, this is moving toward the Pacific plate. This is moving away. We've got divergence here. They're not typically at 90-degree angles to one another. Movement is not now. Okay. Look at the geometry of plate boundaries. So these are two plates in a block diagram. The motion of these two plates varies as they continue to move apart. You have spreading along this orientation, but as the boundary changes orientation, plates move horizontally past one another, and that's your transform boundary. Again, transform boundaries link other type of plate boundaries, such as two spreading centers or a spreading center with a subduction zone. More with geometry, we can observe how the motion between the North American and the Pacific plates varies as the boundary changes orientation. So this is convergence. This is Alaska. If we look further south, we get a transform boundary. Call that the Queen Charlotte Fault. We have plates moving horizontally past one another in this area. As that boundary bends, it becomes convergent. That's the Pacific plate being subducted beneath North America. And now this, the Earth's magnetic field. So we have the liquid outer core that contains convection currents, energy, movement. This is a normal magnetic field. Okay? This is representing a reverse magnetic field. And back to the core. The Earth's inner core transfers heat or less dense material to the liquid outer core. And then we have those convection currents in the outer core. Movement of the molten iron in that area is affected by the Earth's rotation. and it produces electrical currents and a magnetic field. It currently flows from south to north. That is normal polarity. But many times in the past, the magnetic field has flowed from north to south in reverse polarity. And we see that recorded in the rock record. We can observe magnetic reversals as new crust is formed at mid-oceanic ridges or mid-ocean ridges. So the red here is normal magnetic polarity. The white is reverse magnetic polarity. At time 1, all the material being formed in the rock record records normal magnetic polarity. At time 2, we have reverse polarity. And this material is now found on the outer edges, moves away from the ridges. So this is like a new event under a new magnetic field. Over time, this keeps happening. So you build a series of magnetic stripes over time. Now, it doesn't actually look like stripes if you were to look at the rocks. It's a representation of reverses in the Earth's magnetic fields. Okay, so with that, we can have measurements of positive magnetic anomalies over time in the Earth's magnetic fields, and then negative magnetic anomaly as well, and represented at present. We have the age before present in millions of years. Normal polarity plots high on this graph. That's a positive magnetic anomaly. The weaker signal is reverse polarity. That's a negative magnetic anomaly. Seafloor patterns can be compared with patterns on the magnetic time scale to assign ages to each reversal. And we can get generalized patterns of reversals. So these rocks at present are here. These rocks represent 1 million years prior. These would be 2 million years prior, spreading from center, and then 3 million years prior from the spreading center, and then 4 million years prior. If you want to calculate the rates of seafloor spreading, what you'd have to do is know the width of each stripe and the time duration to give you the rate. So that'd be like distance over time to give you the rate. Okay. Another way to test the theory of plate tectonics is to look at the age of the seafloor and the thickness of sediments that are found away from a mid-ocean ridge. So these are drill cores that this research vessel took out of the ocean floor. And what we have are basalt at the base of the drill core, and then sediments that came in later on top and were deposited. The seafloor is youngest near the mid-ocean ridge, where it was just produced, and it's going to be made out of basalt. The age of the seafloor increases away from the ridge, and the sediment thickens away from the ridge because it had more time to accumulate. You have this basalt moving out, and the sediment thickens in a predictable pattern. I mentioned the Hawaiian Islands at least once. How did those form? We have here lines of islands and underwater mountains. We call those seamounts. These chains form when a tectonic plate moves over a source of magma in the mantle. We call that a hot spot. A volcano forms over that hot spot. As that plate continues to move, the volcanism shuts off because the hot spot is relatively fixed compared to the plate, the source for upwelling magma and the source for what built the Hawaiian Islands and the seamounts that are behind them. the plate subsides as it cools. So you've got these islands, but over time they disappear back into the ocean. Nothing is forever. So the Hawaiian Islands are explained by tectonic plates or the Pacific plate moving over a hot spot, volcanism occurring, and it's connected to all the islands that came before it. This one being shown as 28 million years ago, then 10 million years ago, then 5 million years ago, and the big island still forming today, thank goodness. So why is South America lopsided? Now, I never thought of it that way, but that's how the book puts it, so we'll work with that. It's different on this coast versus this coast, so we'll call it that. Can you envision a cross section, a slice from the western part of South America to the mid-Atlantic ridge? Envision it. It would be higher up here, and there's a trench here, and then there's a lower point and a large continental shelf all the way to the ridge. This is what it should mostly look like. It's a cross section, but it's also a block diagram so we can see the surface a little better. So you have a high point here with the subducting slab. You have a passive margin where nothing is going on here. And then you have a spreading center with the mid-ocean ridge. Like I said. So this is the evolution of South America. In the middle Mesozoic, 140 million years ago, you have rifting on this side and then movement over here, away from Africa. All right. Further movement that way until we focus in on the present with the mid-Atlantic ridge here. I kind of wish we could look more at the subduction on the side with the Andes, but here we are with the mid-oceanic ridge in the center. So it began this way and evolved to look something like this. And we'll stop here for this chapter.